Guys, welcome to my YouTube channel. Bala Mugish is my name, and today we are talking about uh, the exploratory data analysis. So let's dive into it, and we're going to perform it using Google Colab. Yeah, the online tool that helps us, of course, clean the data and also train our models. So first things first, we uploaded the data set that we got from UCU, and of course the data was provided by Scania Tracks. To begin with, we are dealing with a project that talks about the air pressure system. Yeah, so the air pressure system is a critical component of these heavy trucks, whereby it is responsible for both braking and gear changes. So yeah, that's the data set we're using, and we're trying to predict when these failures can happen before they actually do happen. Yeah, and that could of course save us from unnecessary mechanic checks. Yeah, total breakdowns and also the maintenance costs. Yeah, so hope you have a brief idea of my project, so we can start on the data cleaning. So the the data we got, or the data we're going to use to train our model, is a CSV file, and they provided us with the training data and also the test data. So we are doing the EDA on the training data first. So the first thing we did was to upload a CSV file in our Google Colab notebook. So that's the command from google.colab import files, then uploaded files.upload, enabling us to choose the CSV file from our local machine to the online Google Colab notebook. So from uploading the data, the next thing was to eliminate all the null values. And when I tried looking through, or if I try showing you the data, the way it was at the beginning, it had a lot of null values. Yeah, and whoever was actually recording the data put a string NA, which is not, of course, recognized by either Excel or CSV to represent null values. So the first thing we did was to change the string NA to none using NumPy, which is, of course, recognized, and yeah, it officially represents null values. So that's the first thing we did in our cleaning process. And yeah, after doing that, we had to print the head. I'm sure you know what the head means. The very first 5 rows that essentially help us to know whether the changes have been effected on the data. Yeah, as you can see, the changes were actually effected. The NA string was, of course, converted to none. Now it's easy for us to visualize and, of course, tell how many missing values do we have in a certain column. Then the next thing was to eliminate columns that have more than 70% missing values. So before we did that, we first drew a heat map. So a heat map basically helps you to visualize the distribution of the missing values of course, the respective columns. So this is the code. We're going to use matplotlib, which is, of course, a library that will help us use these visualizing features. And the title of the heat map will be missing values heat map, as you can see it under plt.title. And df.isna is used when we have a Boolean component, in that uh, the yellowish kind of color will represent missing values, and of course the purple will represent columns, of course, without, yeah, the missing values. So this is the missing heat map, yeah, the missing values heat map. So where you see the yellow, you know that there's a lot of missing values, and where you see the purple, you know there is of course very less missing values. So this can help us to decide on how we are going to eliminate some of the columns. And my decision was we are going to eliminate columns with more than 70% missing values. And I think the bar chart can also show it, because I tried some other method where we are going to sort columns according to the number of missing values they have in ascending order. So as you can see, these first columns have very few missing values, and these columns at the end, of course, have very many missing values. So that's the distribution that helped me, of course, make that decision. Uh, yeah. So then after, of course, I had to save the new data after removing the 70%, after removing columns with more than 70% missing values. And yeah, I saved it as my first clean CSV file. Yeah, to of course avoid confusion. Then my next task, which I decided to do in another notebook, was to do imputation. Imputation, yeah, I mean, I'm going to look for a strategy to fill in missing values uh, for columns that, of course, have less than 30% missing values. Yeah. So I'm going to do the imputation using either, you can use either mean, median, or most frequent value, but I chose median according to, of course, the kind of data I had. Yeah. So that is what we're doing next. The imputation. So I did my imputation using mean. Yeah, I used mean for my imputation. And okay. And you can see the scaffing has refused to go off. Wanted to show you. Oh, okay. Yeah. So you can see from here that this is the data that has been imputed, yeah, with median. So this is the code I imported pandas as PD. Pandas helps us to, of course, create a frame DF that can help us do data analysis and comparisons on data. So yeah, that's the use of pandas, and it helps us to also read these CSV files into a certain frame that can help us to, of course, do the editing. So I first found out how many columns have less than 30% missing values, and I found out that all the columns that had remained after removing, of course, the ones that had more than 70% missing values belonged to columns that had less than 30% missing values. I hope you understand that. So yeah, that's the code. We read the CSV file first, then we calculated the missing percentage by bringing in a variable with variable name missing percentage, and df dot is now dot mean is helping us to check uh, the average of missing values in each column. Then another variable called columns with less than 30% missing was equated to missing percentage, but then with a criteria or with a constraint of missing percentage less than 30. Yeah, so we are looking at the missing percentage, but of course, focusing on columns with less than 30%. Then, of course, you're going to print columns with less than 30%. And like I told you, we found out that all the 161 columns that had remained after doing the elimination of columns that had more than 70% missing values. So out of the 171, now we have 161. That means we dropped 10, and all the 161 that are remaining have less than 30% missing values. So the imputation, like I told you earlier, is going to be with the use of median. So we calculated the median of every column. Then where we had a missing value or where we have none, that of course was done in the very first steps using NumPy, changing the string NA to NaN, which is like officially recognized by Python and Google Colab. Yeah. So wherever we have none, we're going to replace it with the median of that specific column. So that's the procedure. We calculated the median of each column, then filled it in places where we had none. Yeah. So that we can, of course, remove or get rid of the empty cells or columns that have missing values in their cells. So after that, we go straight to our last step. Yeah, and of course I had to save and go to the other notebook for is my work or to make my work easy. So our last, no, not actually our last, our second last. This data set is comprised of 60,000 samples, and they are classified, or they have a column named class that has positive and negative. Positive means that these tracks had failures, but those failures were not necessarily brought by either air pressure system failure. So the problem why they broke down was not because of the air pressure system getting problems. Then the negatives are classifying failures caused by APS. So the negatives actually have more examples. They have 59,000 examples. And surprisingly, the positives have 1,000, of course, giving us a total of 60,000 samples. So you realize we have an imbalance, and an imbalance always, of course, gives us bad models, in that there's always a bias as we are learning. So we want to eliminate a bias because the model actually gives more credit or learns based on or basing on samples that have higher data. Now, in this case, it will learn more on the negatives, and it will to learn less with the positives. So, of course, that will give us a very bad model that will predict very annoying things and very inaccurate things, which we don't want. So, we have imbalancing, and we can actually balance this data using resampling techniques. So the resampling techniques we have up sampling and also down sampling. In that we're going to down sample the negative examples from 59,000 to say 2,000, and also up sample the positive examples from 1,000 to 2000 so that they can balance. Take for instance, you're trying to like build a system that of course predicts spam or not spam emails. There's no way you're going to give it examples or feed more examples on maybe spam email and maybe you give it like an 80%, then non-spam you give it 20%. So surely you see that the model is actually not learning well because the data set is so imbalanced. So it's better it's like a 50-50. That's when it can work out very well. So back to this, I chose 2000, and that's what I'm going to do. So of course the fact that I'm using a new notebook, I had to first load the CSV file. And as you can see from here, I tried counting or did the counting of the positive and negatives, and this is what I got using of course class count, df, and focusing on class only, the very first column. And of course I got 59,000 and of course 1,000. So we're going to do the down sampling. So like I told you, our main goal is to down sample the negatives to 2000. So I'm going to introduce a variable called neg and give it a data frame class. So I'm going to pass on a string neg so that I can easily get it from the CSV file. And I'll do the same for positives, whereby I'm going to introduce a positive variable, put it into a new data frame, focusing on the first column class, and assign it a string positive so that I can easily identify it. So then the random state 42 is for ensuring reproducibility. So I want when I sample again, I actually get the same things. So that's why I have random state 42, then replace is equal to false. In case I find neg in my data set, if I'm supposed to downsample, if I've already reached the limit, then I'll leave it. If I haven't reached the limit, then I'll erase it. Then for upsampling, I'm going to upsample until I reach the limit of 2000. So yeah, I later on I'm going to continue iterating through and then checking if the data frame is balanced by of course getting the relationship between the class counts of the first variable that I named to be positive and the second variable that I named to be negative. That is neg and POS, which is positive, of course. Then after that, you can see that both the negative and positive classes are actually balanced right now because we have 2000 samples for each of them. So that's like a 50-50. So yeah, to avoid spelling my work at the end, I have to like save as I'm going to my last step. So yeah, I had to save that work first and got another Google Colab notebook. Yeah, because it was actually disturbing me, so I had to look for a way because I think I've done this idea for like 4 times. But this technique, of course, helped me to easily uh, yeah, handle. Then uh, we got the last one. So in our last one, we are doing what we call feature scaling, and this is of course very interesting. So feature scaling basically will help us to do what you call standardization. Yeah, and of course, the very first thing we do is to import the fact that we are using a very new notebook. We have to first import the CSV, use pandas to get the data from for it. Then we're using a library called SK Learning Preprocessing, and we are importing a feature called standard scaler that is going to help us do the standardization, or what many call scaling, or what I have termed to be feature scaling. So feature scaling basically will work on only numeric features in the dataset. And we are going to use the scalar as a variable that we passed on the standard scalar, and we are using pandas as PD to create a data frame that can be used for data analysis, yeah, and comparison. And we're going to create an instance. So the main goal is to create an instance of a standard scale used to feed and translate numeric columns and have them between the mean of 0 and the standard deviation of 1. Yeah, I think when I show you the data, it can actually make more sense. So of course, like I told you, we're going to focus on only the class, the column class that has. No, we are going to skip the first column class because it has classifications, negatives and positives, but the other columns have numeric values. So that's why we're going to impact the change on. So this is a sample now. So this is a sample of the data that has been standardized. Yeah, isn't this interesting? So this is our very last step. And when I try printing the head, they still show me that the data has been changed. And from here, they had put class negatives and positives as a last column. So I had to switch it to be the very first column so they can easily know whether it's there or not. Yeah. And finally, when I downloaded my CSV file, looks like this. Interesting. Yeah, and after balancing it, it looked like this for the 2020, for the 2000 samples. Then from here, I had replaced NA with none. Yeah, I think you can see that. Yeah. Then here it still had the missing values. So those are the steps. Thank you for watching. Don't forget to like, follow, and subscribe. My name is Bala Mugisha, working on the project air pressure system. Yeah, and in fact, our lecturer told us to name it reinforcement learning knowledge distillation multi-class APS for predictive maintenance. Yeah, so whatever name makes you happy, yeah, you can call it that. Yeah, have yourselves a good life. Bye.